In lab, you guys noticed that the temperature stopped changing between two objects when they reached the same final temperature. You also noticed that the warm object got cooler and the cool object got warmer in every case. However, they didn't always change by the same amount, and that depends on a thing called specific heat or specific heat capacity. And basically, the higher something's specific heat, the harder it is to change its temperature, or the more energy is required to change its temperature. So water with a specific heat of 4.18 joules per gram degree Celsius, that literally means I have to add 4.18 joules of energy to heat 1 gram of water by 1 degree Celsius. Iron, which has a much lower specific heat, I only need 0.449 joules of energy to heat 1 gram of water by 1 degree Celsius. So it takes 10 times as much energy to heat up 1 gram of water as it does to heat up 1 gram of iron. And the opposite is also true. If we were to cool down 1 gram of water, it would release 10 times as much energy as cooling down 1 gram of iron by 1 degree Celsius. So these units here, they're actually telling you how much energy is contained or required in an object due to its temperature or a temperature change. Now, we can calculate how much heat has been lost or gained by an object using this equation, Q equals mc delta T, where Q is heat, that's the energy transferred, that's measured in joules. Mass is the amount of matter present, measured in grams. C is the specific heat of the material, joules per gram degree Celsius. Remember, energy required to change 1 gram by 1 degree Celsius. And delta T, which is the change in temperature. This little symbol, if you've never seen that before, that's the Greek letter delta. It looks like a triangle. It means change in. Okay, so change in T, or change in temperature, and the way we calculate a change, we always take the final or ending temperature minus the initial or starting temperature. So let's take a look at an example problem. How much heat is needed to raise the temperature of 3,000 grams of water by 60 degrees Celsius? Water has a specific heat of 4.18 joules per gram degree Celsius. Whenever you have a math problem to solve, the very first thing you do is you list your variables. Variables are the things that you are told or want to know. So how much heat is needed? Right there you're thinking to myself, I'm looking for heat. The symbol for heat is Q, so I'm going to write Q equals question mark. It is needed to raise the temperature of 3,000 grams of water. That was a mass. M equals 3,000 grams of water. They're telling me here what the substance is, and down here they tell me it has a specific heat. So when they give you a substance, they're also telling you a specific heat, because you can look those up in a table. By 60 degrees Celsius. Raise the temperature by 60 degrees. Delta T, we don't know a starting and an ending temperature, but we do know that the temperature is going to change by 60 degrees Celsius. And then finally, it tells us right here the specific heat of water, C, equals 4.18 joules per gram degree Celsius. Units always have to match. Grams match grams, degrees Celsius match degrees Celsius. So now we can just use our equation, which says Q is equal to mc delta T. Write this in. You always need to write your equation. That way you don't make a mistake when you're subbing in your numbers for your variables. So now I have Q equals m, which is 3,000, times C, which is 4.18, times delta T, which is 60 degrees Celsius. And this is the part where you can go ahead and get a calculator out. I don't need to see that you can do multiplication by hand. All I want to see is that you can set up your equation and use it correctly. So 3,000 times 4.18 times 60 is 752,400. Now, what units do I have here? Well, we took mass measured in grams times specific heat measured in joules per gram degree Celsius times a change in temperature measured in degrees Celsius. So if you look, this gram cancels this gram, this degree Celsius cancels this degree Celsius, and that leaves me with joules. So this is 752,400 joules of energy. That's a lot of energy. That much energy is required to raise 3 kilograms or 3,000 grams of water by 60 degrees Celsius. And that's if it stays liquid. If it actually went through a phase change in between, there'd be some other math to do. A second example problem, and this one we will see a delta T that we're going to have to calculate. Gold has a specific heat of 0.13 joules per gram degree Celsius. That's the first thing it tells me, so I'm going to write it down. My specific heat, 0.13 joules per gram degree Celsius. If 250 grams of gold increases in temp, well, right there, that was a mass, so I'm going to write that down. M equals 250 grams. Increases in temp from 12 to 62 degrees Celsius. These are two temperatures. This is a starting temperature and an ending temperature. So I'm going to take T1, which is my start temperature, 12 degrees Celsius. T2 equals 62 degrees Celsius. How much heat does it absorb? So again, I'm looking for Q. What's my unknown? Heat. All right. So the equation I have for calculating heat says Q equals mc delta T. And I know M, it's right here. I know C, it's right here. But I don't know delta T, so I have to use delta T equals the final temperature, T2, minus the initial temperature, T1. And so then I can take 62 minus 12, and I get 50 degrees Celsius. So now I have a delta T, and I can sub it into my equation. So I have Q is equal to 250 times C, 0.13, times my delta T, 50 degrees. Again, don't do this long multiplication by hand, just use your calculator. 250 times 0.13 times 50 is equal to 1,625. Again, this is joules. Okay. So whenever you solve a math problem, give me this variable list. If you don't have that, you're going to lose points. That's how you know what you know. Give me the equation you're using. If you don't have the equation, then you just have a bunch of random numbers. If you have an extra step, show me the work for that extra step. Show me this where you actually use the numbers that you have, and then square your final answer so I can find it. I don't want to see 250 times 0.13 blah 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 times 50. I don't need to see that. That's what your calculator's for.